So let me take a moment and remind you of something that we learned in the previous unit, and that's the idea how we calculate the torque on a current loop. We gave a formula previously that says the amount of torque on this loop of wire that sits in a magnetic field is equal to the cross product of its magnetic dipole moment and the external magnetic field. So we got to indicate that these are all vector quantities, and I can explain really quickly where that comes from. Let's see, if the positive terminal and negative terminal are as indicated in this DC power supply, then current's going to flow in the direction of this arrow. So current is flowing, well, you can think of it as a three-dimensional drawing sort of, right? So you can think of the current as being into the page. So if you point your thumb into the page and then you point your fingers to the right in the direction of this external magnetic field, then you'll agree with what's already indicated here, that the force on this segment of wire is downward, and likewise, as already shown here, the force on this portion of the wire is upward. And so the net effect is that there's a torque that causes this loop to rotate in the direction shown right here. So we can say it like this: the magnetic dipole moment we're referring to is just equal to the the amount of current, I, that flows into the loop when multiplied by the area of the loop has a length L and a width W. So when I multiplied the current times the area, I get the magnitude of the dipole moment. If I make a vector that's 1 unit long and points downward, hopefully this drawing isn't getting too busy. There's a vector 1 unit long pointing downward. We can call that the normal vector. That vector lies perpendicular to the plane of the loop. So when I multiply times a unit vector, then I don't change the value of the quantity, I just turn it into a vector. And so the magnetic dipole moment in this case is a vector that lies parallel to that unit normal vector and points downward. By the way, and I think you'll agree with this statement, if you were to rotate, if you use the right-hand rule and you rotate this vector mu into the vector b, I think you agree that that produces a rotation in this direction. So just trying to refamiliarize you with this quantity known as magnetic dipole moment, and inform you once again that an external magnetic field has the ability to exert torque on any magnetic dipole moment. If you want to summarize that, you can take a look at this diagram related to the right-hand rule, which basically says anytime current flows in a direction that would be described when viewed from above as clockwise, there's a magnetic dipole moment, or if we want, we can just say there's magnetism that points in a downward direction. And when the eyeball looks down on the current loop, if we express the current as counterclockwise, then the magnetic dipole moment or the magnetism both point upward. Well, that brings us to this new topic called the Bohr Magneton. Here's a form of current loop on an atomic level. In the hydrogen atom, there's just one proton in the nucleus, and then there's just one electron in orbit with some tangential velocity in a circular path. So because the electron is negatively charged, an eyeball that's looking down on this would say that this electron is orbiting in a counterclockwise direction, yet the conventional current is described as clockwise. And so that's why the magnetic dipole moment for this atom points downward. What I'd like to do is come up with an equation that we can use to calculate exactly what value is the magnetic dipole moment of this hydrogen atom. Okay, so whatever that is, we'll call it mu subscript b, and the b here is a reminder of the Bohr model of the hydrogen atom. So the Bohr Magneton is the value of the magnetic dipole moment associated with an electron orbiting in the hydrogen atom. So first of all, we'll just refer back to what we stated earlier, that magnetic dipole moment is the product of current and area. So let's make that step number 1 of a derivation. Current times area. Now current is equal to is measured in coulombs per second. It's the rate of flow of electric charge, and what's flowing in this case is an electron. So we can say that the Bohr magneton is equal to the charge of the electron. The full charge of the electron makes it all the way around the circle in one time period. So charge per unit time is the charge of the electron in the time of one rotation. And the area is the area of a circle, so that's pi r squared. Now this tangential velocity, it's a constant speed. The electron doesn't speed up or slow down as it orbits. It's just changing direction all the time. So the dirt equation says distance equals rate times time, or in other words, the period of orbit should be equal to the distance around the orbit, which is the circumference, 2 pi r, divided by the orbital speed, which is the v we indicated in the diagram. So step 3 says the value of the Bohr magneton is pi times q times r squared, right? Pi q r squared divided by 2 pi r over v. And then we can cancel some terms. The pi cancels out. One of the r's cancels out. So in step 4, we'll state this as Bohr magneton is equal to qvr over 2. Now, the electron that's orbiting has both charge. There's the charge of the electron and there's the mass of the electron. And whenever you have mass and velocity, you have momentum. Momentum is just equal to mass times velocity. And anytime you have momentum along with a lever arm or a radius, then you have angular momentum. So you should recall that angular momentum is just the vector cross product of the lever arm and the linear momentum. So in magnitude, the angular momentum is mvr. Or, in other words, the r we have right here can be substituted with angular momentum divided by mv. So let's do that. The Bohr magneton is equal to qvl over 2 mv. And now the v cancels out, and we can say that the Bohr magneton is equal to q over 2m, of course this is the charge of an electron and the mass of an electron, times the angular momentum. Now here's where we have to bring up something from quantum mechanics. So if you take physics 4C, you'll learn about this. If you already had it, then this might seem familiar. We see that the electron has a velocity, it has a charge, it has a mass, it has a lever arm, it has a magnetic dipole moment. What you might not realize is that the electron has a wavelength to it. So we refer to that as the electron's de Broglie wavelength. And it's beyond the scope of this lesson to derive this expression, but the de Broglie wavelength is equal to the momentum, it's related to the momentum, it's equal to Planck's constant divided by the momentum. And another quantum result is that the angular momentum is equal to Planck's constant, here symbolized by a lowercase h, divided by 2 pi. Okay, so you might not know where this comes from, but if it is the case, you see it allows us to make a substitution. So working through our derivation in step number 7, we say the Bohr magneton is equal to Q times H divided by 2m times 2 pi, or in other words, QH over 4 pi m. So let's evaluate. The Bohr magneton is equal to, what's the charge of an electron? 1.6 times 10 to the negative 19th coulomb. I don't know if you're familiar with Planck's constant or not. It's 6.63 times 10 to the negative 34th joule seconds. Don't need to explain 4 or pi, and you probably know the mass of the electron is 9.11 times 10 to the negative 31st kilogram. Well, grab a calculator and see if you agree that the value of the Bohr Magneton is 9.27 times 10 to the negative 24th, and then I leave it up to you to verify that the units do indeed work out to be amps times square meter. They better be amps times square meters because we started our derivation in the first step with the definition of magnetic dipole moment being a product of current and area. Now, one last thing about the magnetism associated with the orbit of an electron. There's the nucleus. There's the electron. It's orbiting in a circular path, and so it has this orbital velocity that's tangent to its path. And indeed, this value of the Bohr Magneton is a value we calculated based on the orbital angular momentum, but an electron also has a quantity known as spin. Now, if you want, it's not quite right to think of it as the electron spinning like a top on its own axis, but mathematically it behaves as if that's what electrons are doing. And so there's an additional magnetic dipole moment associated with the spin that's roughly the same as the value of the Bohr Magneton we just found associated with the orbit. However, you know this, that electrons, as they start to fill up shells in other atoms besides hydrogen, now they pair up, and an electron that has spin down will pair up with another electron that has spin up, and so the net effect is that there's no overall magnetic dipole moment due to the electron spin when electrons pair up. So that's the introduction to the Bohr Magneton, and it will come in handy and be useful in our description of something known as magnetization and how that relates to both paramagnetic, diamagnetic, and even ferromagnetic materials. So that's our next lesson.